Following on from the previous two videos, I hope you can accept that. I hope you can accept. I hope you can accept that that sine of x is equal to sine of x plus the app and then minus the app. So if you have this, let's say sine of x here. Let's say this is our an here. So this at n here. This is our an. So it's saying an. I hope you can accept that an plus the magnitude, so this is the magnitude of an here, plus if you add the magnitude, that will then take you back to 0, and then you take away the same magnitude, that would take you back to an. So I hope you can accept that sine of x is equal to sine x plus app minus app. So that's like saying, I hope you can accept that this is equal to an and then plus the absolute an, and then you take away absolute an. I hope you can accept this. So if you have an alternating series like this, for example. So this is so if you look at this an, if you have an plus absolute an, it will look like this. It will look. Remember, when it's negative, it will go to 0. When it's negative, it will go to 0. When it's negative, it goes to 0. When it's here, it's going to be twice as much. So if you look at this, hang on, absolute here. If you look at this here, it will look something like this, down to here, and then it would be 0 here, and then it would be up here, and then it would be 0 here, and then it would be up here, and then it would be 0 here, and so on. So I hope you can accept that. So going back to the proof. So we were here. Remember, this thing here is always positive. The reason why we're doing this thing here, hang on. The reason why earlier we were down here, and then by doing this, you push everything up into the positive realm. You push everything up into the positive realm. Now this thing here is always above 0. It's always above 0. So because it's always above 0, then we can use the direct comparison test. So looking at this here, so this thing here is always positive because it's bigger than 0, but it's less than this thing here. So when given this, hang on, when given this 2 absolute an here, because this is a constant, you can actually take it out here and just concentrate on this alternating series. Now, if this thing converges, then the 2 an must also converge. So if this thing converges, then 2 must also converge. So looking at this here, remember we're saying if the absolutes here converge, then this will also converge, because this is above 0, this is also above 0. So if this thing here converge, remember the theorem is saying, hang on, going back to the original theorem. The original theorem saying if, so it's saying if this thing here converge. So it's saying if this thing here converge, then by the way, sorry, if this thing here converge, then 2 an here will also converge because it's a constant. So it's saying if this thing here converge, then this thing here will also converge. Now this thing here is bigger or equal to this thing here, and they're both above 0. So therefore this will also converge. So this series here, an plus absolute an here well this here will also have brackets. So this whole thing here will converge because if this thing converge, then 2, because 2 is a constant, then this thing here will converge. If this thing here is converged, this thing here is greater or equal to this. Therefore, this will also converge. This will also converge. So now looking at this, hang on. So you remember you can always write an. You can always write an as remember that thing. We can always write sine x equals sine x plus the absolute sine x, and then minus absolute sine x. So that's like this bit here. It's saying an is the same as am plus the absolute and then minus the absolute. You can always write am as this. Now, here's the thing. Hang on. So an is equal to this and then minus this. Well, we've already established that this thing here converge. So you can always write an. You can always write an as this thing here. So you can always write an as this thing here. But then this thing here can be broken up into two separate series. So that's this one series here, one series here. Now it's saying if, right from the start, it's saying if this thing here converge, so therefore this thing here must converge. It's saying if it converges, then this will converge. But then when we were here, if this thing here converged, then this thing here must also converge. This here also converge. So you've got an here. You've got this thing that you're trying to investigate. You've got this thing that you're trying to investigate. But then when you look at the absolute version of this, which is this bit here, if this thing here converge, well, this thing here we've already established that this thing here will also converge, because up here, if this converge, then this will also converge. So you've got something. You've got something that you're trying to investigate. Something that you're trying to investigate can be rewritten as this and this. Now it's saying if this thing here converge, then from here, if this converge, then this will converge. So this thing here must converge. So now you've got something that is made up of something that converge and something that converge. Therefore, this whole thing here, the thing that you're trying to investigate, the series that you're trying to investigate, must also converge. So the point here is that the thing that you're trying to investigate can be rewritten as this. That's like our sine x equals sine x plus apps sine x minus so on. This thing here can be rewritten as this. But then this is really two series. This is really two series. One series, one series. It's saying if this thing here converge, and if this thing here converge, then looking at this, if this thing here converge, then this thing here must converge. So therefore this thing here must converge. So something you're trying to investigate, which is made up of two other things that converge. Therefore the original thing that you're trying to investigate must also converge. Okay, I hope you can follow it.